Right, this is the last little bit about the photoelectric effect, and it's called the emission and absorption spectra. Now, these diagrams that you see in this video can be found on the Google Drive. You'll see it says emission and absorption spectra images. It is a Word document, so once you've edited it or it suits your needs, you can print it out, and every time we do a little part, instead of drawing all of these diagrams, you can basically just stick them in your book so that it's easier and it helps you to get through this a little bit faster. Although you do have to take notes sometimes, we will use the diagrams to make things a little bit easier for you. All right, the first thing that we're looking at is we look at the Bohr diagrams. So we have a guy, his name is Niels Bohr, and you learned about Niels Bohr in grade 10. Niels Bohr, he discovered the idea of electrons moving on orbitals. Right? And he said that these orbitals are like energy levels. And depending on where an electron is situated, it has different types of energy. So let's say, for example, if I'm looking here, this is the Bohr diagram for a nitrogen atom. I know that in the middle, I have my nucleus. Please make sure you add this, obviously, to your diagram. Oops, the printed one. Right? Inside my nucleus, I've got two parts. I've got protons, which have a positive charge, and we can see them, they are in blue. The other thing we have is neutrons, and you can just typex or fix your diagram here. Neutrons are these little red ones, and they have no charge. And then we have the electron, which has a negative charge. Now your electrons are on these electron orbits, or we can call them electron shells. Right? And depending on where you are, you're on different sorts of shells. So if you're on the first shell, those electrons are called core electrons. So if you're on shell number 1, you're a core electron. It means it's very, very stable and fixed. You've seen this when you're doing Bohr diagrams. The electrons that move around, that are involved in bonding, are called, on the outermost shell, are valence electrons. And they are the basis for things like Lewis diagrams and so on. So you've got now, this section is purely physics, but we're bringing chemistry and physics and showing you how these two things work together. So those are the two things we have to know. That first shells are core electrons and outer shells are valence electrons. And we usually use valence electrons for chemical bonding and Lewis diagrams. So you have your pictures, you're just adding on notes. So our main focus today is we're going to look at what are these electrons doing on these different shells and how they move from shell to shell under the right conditions. So when I'm looking at a Bohr diagram, there are 2 or 3 parts that we've got to look at. The first thing that you need to understand is over here, the little part that I'm highlighting, over here, that is called your ground state. Now your ground state is your energy level 1, right? That's your ground state. If your electron that's on your ground state, this one over here, if it moves to a different energy level, it moves away from the nucleus. Right? It is going to absorb energy from a photon. Right? If it gets into a further state, let's have a look at that. If I look here on the outside or past the ground state, that is called an excited state. An excited state means that it has different abilities for things like bonding, or it has an opportunity to gain kinetic energy. Right? So it's an excited state. Right, if an electron was sitting on this excited state over there and it moves down to the ground state, then what it's going to do is it's going to release energy in the form of a photon. That is the idea that we are working with in this little section. Right. If I had to go then and look at what we mean by energy levels, how we're going to refer to the energy levels in this section is we're going to look at them as n is equal to 1, n is equal to 2, n is equal to 3, 4, and 5. Where n is equal to 1 is going to be our ground state. Right? And then you have, which is energy level 1. Energy level 1. And then you can go all the way up to energy level 5. And what happens is eventually we go to n is equal to infinity. Now all that means is that the number of shells is fixed. Right? The number of shells is fixed. But if an electron reaches past, or let's rather say reaches n infinity, n equals to infinity, or past n is equal to infinity, then it is no longer under the influence of the nucleus. Right now, your nucleus, it holds the electrons in position. Right? There is some sort of attractive force that holds the electrons. But if the electrons go too far away, so let's say they start branching out and they start going too far away, right? Then we're going to have a situation called the photoelectric effect. That's essentially what's happening here. So if I go past a certain number of shells, then I'm going to have a situation with a photoelectric effect. Another thing that you're going to hear me saying is this: N1, N2, N3, N4, N5 are called, we call them states. All right? It just means shells. It means levels. But you're going to see me using the word states quite often. And please remember, I've provided you with the diagrams. All you've got to do now is add all of this information next to or onto your diagram to show what I'm explaining here, you're going to need these notes later on. All right, so let's have a look here at this little picture. All right. This is the basic idea of what we're looking at. We're saying that if an electron moves from the ground state, right, and it moves away, then it's going to absorb a photon. That's how it gets there, right? It goes from the ground state up. If it's on the ground state, on the excited, in an excited state, and it moves down to the ground state, then it's going to emit a photon. So the basic idea is these electrons, right, the electrons can move between states given enough energy, or if there is enough energy release. Oops. Right, atoms and molecules can absorb, you should be writing this down, and emit light. Right, they can either take it up or they can send it out. And that will tell us, that information tells us how many different energy levels an electron has and how far apart the energy levels are spread. Energy levels are spread. Right? Now, what we also need to understand is that different colors of light are associated with different photons, or rather we should say photon energies. Right? So what that means, we know a photon, as you've seen in previous videos, is what we call a packet of light. Like, imagine a little bean bag. So let's say, for example, point number 2 here, I had two types of light, red light and blue light. This tells me that a photon of red light, right, will have less energy than a photon of blue light. Now the reason for this is, if I look at their wavelengths, I can see that red light has a longer wavelength. And if I have a longer wavelength, I'm going to get less energy. So you've seen this in previous videos. We understand that idea. Electrons only exist in their shells, right? So that's another thing that we must remember. Electrons only exist in their shells, or rather we should say states, right, around the nucleus. That means that every shell, every state or shell corresponds to its own energy. Now, in an atom, the amount of energy levels that are allowed depend on the structure of the protons and electrons. And let's just have a look at this little setup here. Let's say we must understand how this works. Let's say I just drew a little atom. This diagram is not available to you. That's your nucleus. There's your electron. It's sitting over there. And this is just the next energy level. Alright, so this electron here, let's say we bring in a little bit of light. Comes in. And this has a high frequency. Right, that high frequency light's going to come out of a photon, and what we're going to do is we're going to have this electron moving up here. So now it's sitting on this new energy level. And what we call that is we call that excitation. Right? And when I have excitation, I can say a photon is absorbed. And when that happens, the electron goes up in energy level. Right, so that's the first thing. Then let's just say, again, I have an atom and it's got its one electron and it's got other energy states around it. And let's say I have in another type of photon coming in, and this has got a very high frequency, right? Very high frequency. This electron here has too much of energy coming through, right? And if it has too much of energy coming through, it's going to pop right off and end up over there somewhere. That whole process is called ionization. Now, ionization is when an electron is given enough energy by a photon which causes it to leave the atom completely. Right, so ionization just means, again, photon absorbed. However, this time the electron leaves the atom. And I said that was going to be photoelectric effect. You then have another situation. Let's just say, now once this electron absorbs that energy and it gets to this level here, it's going to come straight back down here. So essentially all electrons prefer being in a ground state. Now, what that means is, when that happens, it's going to return to that ground state and it's going to have something we called emission. So we call that de-excitation, when electron returns to an energy level or an energy state, and we're going to get a photon is emitted. So this tells me about electrons. It tells me two bits of information. One is that an electron can exist on a state or shell, and it tells me that it can exist outside the atom. Alright, so what this Niels Bohr atom that we're going to look at, you've got your basic nucleus, you've got your electrons moving about. It can move between n1 up to n infinity. When it leaves, when it goes up in energy level, it absorbs a photon. When it comes down, it emits a photon. So when this happens, right, when I have, let's say number 5, if I move out, and if the electron moves out or up, it must gain energy. If it moves in or down, then it's going to lose energy. So we need to look at that kind of idea. Now, when we say it's moving down, the lowest energy possible is going to be the ground state. Now, if they give too much of energy, we said there's going to be the electron is going to be ionized, and then what happens is if it will exceed n infinity, and then it just shoots out because it doesn't have any energy states left for it to sit on, so it just goes right past that. So I'm just going to show you a basic idea of how this all works. Alright, so what we're going to be looking at here is we're going to be looking at this atom. If I don't provide you with the image, please make sure that you draw the image, because this is important. So instead of looking at it in the Bohr diagram, what we're going to do is we're going to just simplify our drawing a little bit. And what I'm going to do is I'm going to take out a cross section here of this atom and draw out all the energy levels. Alright, so the cross section that I'm looking at, I've just brought it out like that so it's a little bit easier for us to look at it. So the first thing I've got here is that n is equal to 1. I've got my ground state. And up here at n is equal to infinity, I've got ionization. So that means if my electron ever reaches that point, it's going to leave the atom completely. So let's just look at this. Is just an example or an idea that we're going to work with. So it's the basis of what we're going to be up to. So let's say, for example, these are not real numbers. We will have examples with real numbers. This is just an example. Let's say I have 8 electron volts here, and then over here I've got 6 electron volts, 5 electron volts, 3 electron volts, and then 1 electron volt. Right, those are my different energy levels. So let's just talk about what we mean by electron volt. Right, if I look at this EV, electron volt is the amount of kinetic energy gained or lost. Let me just move this here so we can work with it. Gained or lost by a single electron accelerating from rest through an electric potential difference of 1 volt through a vacuum. Right? Now electron volts, because it's the amount of kinetic energy, it is measured in joules, the J there. And what we're saying is that 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joules, which is something that I think that you're more joules, coulombs, and all that value is the charge of an electron. Right, so essentially, if I had, for example, here 8 electron volts, it's just going to be 8 times 1.6 times 10 to the power of negative 19, and that will give me an energy of 1.28 times 10 to the power of negative 18 joules. Right, so that is what I'm looking at now. Right, I'm looking at this idea of electrons moving through the situation. So the first thing you need to understand here about these types of electrons, let's say, for example, let's work in one color. Let's see a color we don't have. Let's say I had a photon that came through here to this atom. So here's my little photon, and that is a photon. And remember, the formula E is equal to HF. Alright, I've got my little photon here with a certain frequency, and it comes in here. So I have my electron, and my electron is sitting here in the ground state. Now I've had all of this energy that's come through. So what's going to happen now is my atom is going to absorb that energy. So let's just write a little bit of a note here. Let's say it was given the energy of the photon is equal to 6 volts, 6 electron volts. Now if I go here and I say I'm at the ground state at 8 electron volts, and I need to move up now from my ground state, then they've given me 6 electron volts. So that's going to take me 8 minus 6. Let's do that. 8 minus 6 electron volts is going to give me 2 electron volts. But when I look at this zone over here, this 2 electron volts does not exist. So I have a situation now where my electron does not have enough energy to reach 2 electron volts. So if there is not enough energy, that means the light or the photon will pass right through. Right? It will pass right through, which means it is not absorbed. Let's say, so this is the first situation. So that's not going to work for us, right? Let's say instead, this time they give you the energy of the photon at 5 electron volts. So you'll save 8 electron volts minus 5 electron volts, and that takes you to 3 electron volts. But when I look at my diagram here, I can see 3 electron volts. So now I have enough energy to get to n is equal to 4. So this electron can go all the way up here to n is equal to 4 because it was given that 5 electron volts. So that's the first thing we must understand. Now that it's there, or it's up there, now we understand that if I have a photon of light, that comes through, and my atom, let's say here, absorbs essentially 6 electron volts. It is not enough energy, so the photon is going to pass through. If it absorbs 5 electron volts, it has enough energy to move up. Now let's say, for example, let's say our electron is now up here on N4. There's our electron there. It's up on N4. And I said to you that it prefers to be on the ground state. Now it needs to come back. So it has options. Option number 1, it can either go straight from N4 all the way back down, and then it will release a certain color of light. It can go all the way from N4 to N2, and it will release some sort of light. Or it has the option of going from N4 to N3, then to N2, then to N1. So in that instance, I'm just going to make the notes here. It has the option, so on the way down, let's put your number 3, on the way down, it can either go N4 all the way to N1. And what it's going to do, it's going to emit a color of light. Or it can go from N is equal to 4 to N is equal to 3 to N is equal to 2 to N is equal to 1. You can choose any one of these little methods. And what happens then is that from N4 to N3, you're going to get a specific color. From N3 to N2, you're going to get another color that's going to be emitted. If it's emitted, we can see the color. If it's absorbed, we're not going to be able to see it. So what you need to understand about this, and we're going to do a real example and look at how all of this works for a certain atom. What you need to understand or take back from this is that all atoms have unique energies, right? These unique energies give rise to unique colors that can be absorbed or emitted. Now, if they're unique, that means, so when I mean unique, I'm talking about things like turquoise or violet, indigo, the carmine, right, mauve. All of these different atoms, when they have a photon that comes onto them, they're going to absorb different colors. When they move down to their ground state, they will emit a color of light. And each time they go from different energy to another energy, the colors will be different. Colors are different. And that can give us information about which atom I'm dealing with. Remember I said, which atom is this? If I look at what's been absorbed or emitted, I can look at what energy levels, what energy am I dealing with. I can look at how far apart the orbitals are. So those are the types of information that I can take from this. We're going to look at hydrogen in a lot more detail now. So it is kind of intensive. Most of the time, I would say go back, watch this again, and then start with what comes next. Right, the atom that we're going to be working with here is hydrogen. Right, so we're looking at hydrogen spectrum. Right. When we look at hydrogen spectrum, remember what we said? That if it goes down in energy level, it will emit light. And if it goes up in energy level, it will absorb light. So those are the two things we have to look at. Now this over here is the energy levels of hydrogen. So the quality of this photo is not the greatest, but we'll just have a look at how we can work with it. You're obviously going to have to, in your books, draw out the energy levels because we're going to write a lot of information. So this diagram is not drawn well enough. So we can say if an electron sitting just outside of the influences of the nucleus or outside the atom, it must have zero energy. So I can see that here. So there's my electron that's sitting there on the outside. It's been ionized. If it comes under the influence of the nucleus, it will lose energy. That is the reason why each energy value is negative. So I can then have a look here. It's negative. Have a look here. Energy level 1, 2, 3, 4, 5, and 6. All of those values are negative. And the maximum energy that the free electron could lose is 13 electron volts, and that is when it reaches ground level N1 over there. So that is what we are looking at. Please make sure that you draw this in your book. Have a look at the space between each one, each of these energy levels. Use that when you draw your diagram so that you have enough space to work with rather than working on this very cramped diagram. Right, the first thing we're going to look at now is we're going to look at, also please make sure these notes that are here at the bottom, they correspond to this diagram here. So please get that into your books. Right, we're going to have a diagram that looks something like this. You will have one in your book as well. Right, so first of all that you need to understand is up here at the top, we've got n is equal to infinity. And all that means is that the electron is not under the influence of the nucleus. That attractive force doesn't exist anymore. Right, so the first thing that we're going to look at is we're going to look at how this whole thing works for hydrogen. So here's my energy levels. The first thing I'm going to do here is I'm going to convert my electron volts to joules. And remember what I said, to do that you're going to say times, whatever the value is, 1 electron volt multiplied by 1.6 times 10 to the power of negative 19 coulombs. So let's just have a look at how that's going to look. So for negative 13.6, I'm just going to say negative 13.6 multiplied by 1.6 times 10 to the power of negative 19 coulombs. I suggest you do that from energy level 1 all the way up to energy level 6 quickly by yourself so that you can get that practice in. So just pause your video and do the work by yourself. And let's just have a look at a couple of things. The first thing you need to know is that at energy level 1, remember what I said, this is called the ground state. We just put that in so that we remember that. We also know that negative 13.6 electron volts is the lowest energy level there. So let's say I had an electron. I'm just going to give my electron a color here. Let's say I had an electron here. That's my electron. And now I want to get my electron to be ionized. What I've got to do is I've got to take it from level 1 here. And I've got to take it all the way up. Have a look at this. All the way up to n infinity. So this first step that I'm showing here is to get the electron to the ionization. You'll see I use colors. You use colors as well, so you know what's going on. To get it to the ionization point, it needs 13.6 electron volts of energy. And then it reaches that ionization point past or to n infinity and so on. Right, the second thing, we already converted all of our information into joules. Please make sure that your values are correct and that you understand that all of these values, the electron volt values, are negative values. Now let's just look at some information before we get into this. The first thing that we need to know down is that all electrons want to be in the ground state. The goal is to get back there n is equal to 1. Right? If under the conditions they have not been ionized. So it's preferable to stay in the first level. The next thing is all atoms have states at certain levels. Right? Therefore, each atom has a unique state. Unique set of states. What this means for us is that the idea of this unique set is that electrons can only absorb enough energy to land directly or exactly on an energy level or state, right? Or be ionized, essentially, right? That means the first thing, they can jump more than one level at a time. They can jump or move more than one level at a time. That's the first thing. The second thing is, if a photon has the wrong, that's important, amount of energy, it is ignored by the electron. So can you see how specific it is? When we mean wrong, two things can happen. If the energy is too much, it's probably going to go to ionization. And then it will leave the atom. If it's too little or not enough, then it will pass right through. So it will have no effect on the electron. Right? Those are the conditions here. Right, so what we're looking at here in this little energy diagram here is we're going to be looking at absorbing photons. Right. Let's see how we're going to sort this information out. So please make sure these notes are also in your books, as well as everything that we're doing. Let's look at some conditions that will help us to understand what's going to happen on this actual diagram. Let's say the first thing that I want to do is I want to move to n is equal to 2. So I'm going from n is equal to 1 and I'm moving to n is equal to 2. So that's moving up. If I move up, I need to absorb energy. But now I need to look at how much energy do I need to absorb. Alright, so I need to look at that difference. So let's have a look here. Alright, so let's say I have my electron over here. And now I want this electron to go up over here. I want it to go to N2, which is there. Alright, now in order for me to get there, how much energy needs to be absorbed? Alright, so let's have a look here. I'm starting at negative 3.6 electron volts at n is equal to 1. And I need to move to n is equal to 2, which is sitting at negative 3.40 electron volts. So I am absorbing energy. So I do a little sum and I look at the change in electron volts and I go negative 13.6 plus 3.40 and I get a total of 10.2 electron volts in total. So the amount of energy that my electron must absorb to go from N1 to N2 is 10.2 electron volts. We can convert that by multiplying it times 10 to the power 1.6 times 10 to the power of negative 19, and that gives me 1.63 times 10 to the power of negative 18 joules that you would need to gain in order to move up. Alright, so that's the first thing. Now, another thing that's worth noting is that if you were given 10.3 or 10.4 or even 10.19 joule electron volts, this would be no effect on the electron at all, because electrons have to be on a state. They cannot be in between. Alright, so make a note there. No in between energy levels. And if this happens where they've given you 10.3 or 10.4, even they give you 10.6, that's going to be the photon is ignored and it passes right through. So let's have a look at another little condition. Let's say for number 2, they say, given a photon of energy at 2.65 electron volts. Let's have a look at how that looks. So at the moment, your electron is at negative 3.40. And that's at n is equal to 2. But now we add on 2.65. You pop that into your calculator and you're going to get 0.75 electron volts. Now if I go back to my diagram, have a look here. It goes negative 3.40, 1.51, 0.85. So you've got now 0.75 electron volts. That is in between, right? It's in between n is equal to 4 and n is equal to 5. Therefore, the photon is ignored. Right, so all I'm going to say there is, if I was given this condition of 2.65 electron volts, I could say that the photon has inefficient energy, and therefore the photon will pass through the atom. Right? In the same instance, let's say they gave you, let's say what was given to you was 2.55 electron volts. So now you're sitting on N2, N is equal to 2, and negative 3.40 plus 2.55 electron volts, and you can see the math there. I'm going to get 0.85 electron volts. So now I've got to take this value, I've got to go look at it and see where is my photon going, where is my electron going. So if I'm looking here, my electron is over here, and at 0.85, it's up here. So that's where I need it to go. It's going to go all the way up here to n is equal to 4. And that whole move means it had to gain 2.55 electron volts gained in order to make that move. So every time you add in or you give the electron more energy, it absorbs that energy and then it moves to N4. Let's have a look here now at condition number 3. Let's say we give it another condition. And this time we say, given more than 0.85 volts, right? Electron volts. Now, if I'm given more than that, just have a look here. I'm going to be given 0.85. So if I say negative 0.85 plus, let's have a look here. Let's go back to that condition, sorry. If I've got negative 0.85 plus 0.85, I'm going to end up with 0 electron volts. And the only way I can end up with that is it means that my electron was ionized. That means it's left the atom completely. So I can say that any photon that was able to put the electron at n is equal to infinity or beyond that would be absorbed. So if it's at N8, it's going to be absorbed. And if it's beyond that point, then the remaining energy is converted to kinetic energy. And that kinetic energy is responsible for movement, and we spoke about this, that movement will allow it to have the photoelectric effect. For example, let's say I was given at this point, at n4, at n is equal to 4, I was given 1 electron volt to the electron. Right, let's see what would happen. 0.85 electron volts will be used to ionize the electron, right, at the point n is equal to infinity, right, and the remaining 0.15 electron volts would be converted to, or rather into, kinetic energy, so it can move off or out of the atom. And that is the kind of setup you had. So let's say I did give it this 1 electron volt, and I'll use or I gave it this, rather let's say I gave it 0.85 electron volts. What my atom would then do is, from this point here, oops, I'll do that. From this point here, it would make its way up here onto that little zone over there, n is equal to infinity, and that is where it will be ionized. So make sure you've got all of these conditions, that you've edited your diagram, and that you're seeing here how we do the calculations to see how much energy has been gained, how many, we're going to look now at how much energy has been lost. The other thing that you can do is you can also be asked to work out wavelengths. So I'm going to show you that in a bit as well. Let's have a look at the next thing. The next thing is looking at emitting photons. You also need to redraw this diagram because we're going to do a whole bunch of other things on it. So we're still working with hydrogen. Still the same. All our values are the same. I'm not going to convert the electron volts to joules for this one because we've done it already. I just want to have a look at how the electrons move, what kind of information we're going to need for something like this. So the first thing that we need to identify or understand is, let's say for example I have an electron and that electron is sitting on N5 over there. Right, so what's going to happen is, remember what I said, an electron, let's use another color, an electron on N5, n is equal to 5, would prefer to be on n is equal to 1, which is the ground state. Now in order to do that, the electron, right, the electron must lose energy. Right, it must keep losing energy in order to move down. Now when it does that, let's make a note here, an electron must emit photons with exactly the right amount of energy for them to land directly on an energy level, or be ionized. Right, two things to note. They can move more than one level at a time. Right, but here's the thing, the big but about emission. There is only a certain combination of photons or certain photons it can release. This is talking about each atom. So that means that each photon will give off a different color. Alright, so it's not, this one is not infinite. In other words, every single atom only gives off a certain amount of colors. So I'm going to see only certain bands of color per atom. That's how I know which atom it is. So let's have a look at hydrogen. Right, if I'm looking at hydrogen here, and I have my rules for hydrogen, let's just have a look here at how I would state that. Let's put some rules in. Number one, the first thing is the lowest or the minimum amount of energy possible for this atom to emit a photon. You can have 0.3 electron volts or 4.8 times 10 to the power of negative 20 joules of energy. Now if I look at all of these levels, I've got to minus them. So if I go 3.40, if I go from N2 to N3, then that doesn't give me 0.3. So what I'm looking at is, if I go from N5 to N4, let's have a look at what that's going to look like. If my atom moves from N5 to N4, oh, very small margin there, I would have, let's have a look here. So N is equal to 5 to N is equal to 4. I've got a loss of energy of 0.3 electron volts, because at 5 it's 0.54 and at N4 it's 0.85. So 0.85 minus 0.54 is equal to 0.31 electron volts. Now that is your smallest change that can make. Let's say, for example, number 2, let's say if it released a photon of energy equal to 0.97 electron volts, which is about 1.55 times 10 to the power of negative 19 joules of energy from that point. So if I'm looking at N5, N is equal to 5, it's sitting at 0.54. And what's going to happen now, it's going to release or give away 0.97 0.97. So minus 0.97, and that gives me negative 1.51. Now, if I look at negative 1.51, that corresponds here, see here, to N3. So now I've got my electron has moved this distance, and it's released 0.97 electron volts to reach N3. So if I had that much of released, I would go from n is equal to 5 to n is equal to, and let's have a look where that reached us. N is equal to 3. Sorry, let me just change that a little bit. I go from here to there. That is the kind of thing that I am looking at. If I look at condition 3, and let's say this one's the next one. This is the maximum possible photon of energy emitted would be 13.06 electron volts, which is about 2.09 times 10 to the power of negative 19 joules. And that would be a single jump from n is equal to 5 to n is equal to 1. So let's have a look at what that would look like. Let's go up here. From n is equal to 5 all the way down to here. And you've released 13.06 electron volts. So here I can say negative 0.54 minus 13.06 electron volts, and that will give me 13.6 electron volts, which leaves me at n is equal to 1. So two things to take back from here. We've got the maximum possible, which is 13.06. Remember, hydrogen is the most common question. And we've also got our lowest and minimum at 0.3 electron volts. And all of this, remember, we said will be, can only emit or absorb one photon at a time. And so what they can ask you to do is they can ask you to calculate the wavelength of the photon released by an electron moving from, let's pick n is equal to 6 to n is equal to 2. Right, that's the question. The first thing that you're going to need with you is you're going to need your little table from grade 10 that they show you, so that when we work out our answer, we can see if I have a certain wavelength, what kind of color I'm going to get. So basically, I've got an electron here on n is equal to 6, and I'm going to take that electron down to n is equal to 2, and it's going to emit a photon, and that photon is going to have a certain color. Right, so let's have a look at how that gets sorted out. Right, the first thing we want wavelength. So the formula that we use for wavelength is E is equal to 8c over lambda. H I've got, C I've got, I need lambda, and then I need energy of the photon. So the first thing that you need to do is I know that if I have an electron at N6 and it goes from N6 to N2, then I know it must lose energy, right? And if it loses energy, I'm going to get a photon being released. So I'm going to say that E, which is my emitted photon, is equal, should write this down, to the difference in energy between the two energy levels, Alright, so I'm going to say E6 minus E2. Now, in this formula, you must substitute in joules, not electron volts. Alright, so first we need to make sure we do all of our conversions. So if I look at n is equal to 6, I've got negative 0.38 electron volts, and n is equal to 2, I've got negative 3.39 electron volts. So the first thing I need to do is do a different sum between the two of them. So I've now got, alright, so all I'm going to do is I'm going to say negative 0.38 minus 3.39 is equal to, and I'm going to get 3.01. Alright, so I've got that situation, and then I know that's in electron volts. But I know I can't substitute electron volts, so I'm going to convert that. I'm going to go 3.01 times 1.6 times 10 to the power of negative 19. So you must convert to joules. And that's going to give me 4.816 times 10 to the power of 19 joules. And that's my E value. That's going to go into my formula. Alright, so all I'm going to do now is I'm going to write down E is equal to HC over lambda, where E is equal to 4.816 times 10 to the power of negative 19 multiplied by 6.63 times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8. That's my H and my C, all over lambda. And then, not times, it's equals to, sorry. And then that's, lambda is then equal to, and that gives me 4.13 times 10 to the power of negative 7 meters. Now, I need my answer to be in nanometers. So I'll say 4.13 times 10 to the power of negative 7 divided by 10 to the power of negative 9. And that's going to give me a total of 412.99 nanometers. And let's see where that falls. So if I go up here and I'm looking at the number, let's say 413, just rounding it off. That corresponds to 380, between 380 and 425, 380 and 425. So therefore, go back down here. Therefore, the wavelength is 412.99 nanometers, which corresponds to violet light in the emission spectrum. So that means when I look at hydrogen, this is a summary of what hydrogen is going to give. So essentially what's happening is, for example, my brain or your brain cannot see all colors at once. So your brain, and sometimes it can't see certain colors. So your brain, when it looks at a certain color, it breaks that color up so that it's into a color that is easily seeable by us. So hydrogen, for example, if it went from 6 down to 2, it would give me violet light. If it went from 5 to 2, it would give me a blue. If it goes from 4 to 2, it gives me a kind of a greenish, bluish, turquoise. And if it goes from 3 to 2, then it gives me a red light. So this is a good little summary. It's not in your images that I've made for you. You'll just have to just draw it out quickly, just a little summary. All right, over here what we have is what we call a spectrum of light. So when we look at a spectrum, it's a band of colors consisting of different components of light according to the wavelength that is seen through a spectrometer. Now when we look at a continuous spectrum, we've got red, orange, yellow, green, blue, indigo, and violet. Those are your colors of the rainbow. If you notice about this spectrum here, is there are no gaps or breaks. So it's quite a smooth kind of display. This is called visible light, and it's on your electromagnetic radiation spectrum. Now all of this is measured with a spectrometer, and it's used to study the absorption and emission of light. A continuous spectra is also called a thermal or black body spectra, arise from dense gases or solid objects which radiate heat. They emit radiation over a broad range of wavelengths. Thus, the spectra appears smooth and continuous. So if you notice about this spectrum, there are no gaps. We can see each color and how it transitions from red to orange to yellow to green. We can see the full spectrum. Now, when I have something like absorption or emission, then that spectrum is no longer continuous. When I see absorption, right, there's going to be no color. So we're going to have black bands inside the spectrum. When I see emission, I'm going to see color bands. And these color bands are very specific to the colors emitted by that specific atom. What that means is whatever color is emitted, we will see the color, right? But the rest of the band would be black. Right? You won't see any color. You're only going to see, so in your absorption spectrum, you're going to see mostly black black bands, whichever color was absorbed, right? But then you'll see the rest of the spectrum. The spectrum in color, right? So wherever it gets absorbed, you're going to see no color. Emission, wherever you see emission, it's going to be in color. Let's have a look at the next thing. In the later half of the 19th century, something remarkable was being noticed by a few scientists. So, what they looked at was they said that energized elements would emit specific visible colors of light, and the colors were specific to that element. But no one knew why this was happening. For example, if we energize hydrogen gas with an electric current, the H2 molecules will split into hydrogen atoms. So if I'm looking here, I'm just going to use a color. Over here, I've got that photo tube, and I'm going to energize H2, hydrogen gas. Right, energize means that I'm just going to use with an electric current. Right, and what's going to happen is that the H2 molecules are going to split into two hydrogen atoms. So I have high energy and I have a current. So that is what's happening in that little tube. And when this happens, those energized hydrogen atoms emit a specific color, or rather, they have a specific color spectrum that we've seen so far. So if I have this little bit here, this is the color that comes out. This is the color we cannot see, right? But we know that hydrogen has a color spectrum of 4 colors. And we looked at that in the previous slide. Now, our nervous system, however, is not able to see the 4 individual colors. So our brain integrates those 4 colors into one specific color, and that's the color that we see. So, but when we diffract it, so let's just go here. When we take that pink light and it goes through a process of diffraction. Diffraction just means the bending of light. You would have done this in grade 9 at some point. Right? We can see, what we're doing is we're going to end up splitting hydrogen's pink color. When we do that, we can see the colors that are being emitted by hydrogen atoms, which is over here. Let me just make a note of it. We've got over here, we've got violet. We've then got over there blue. We've then got over here a blue-green, so like turquoise. And then at the end over there, we've got red. And those are the colors all at specifics wavelengths. Alright, so essentially what's happening now is we've got ourselves here an emission spectrum. So you can see that for hydrogen, I've only got these 4 colors that are going to come out at the end of the day. So this is what we call the emission spectrum. So all we're looking at with the emission spectrum is the specific colors emitted by an energized substance. That energized substance is some sort of hot gas. So it's a gas. Let's just have a look here. It's a gas that's heated up, and then that gas goes through some sort of prism. That's what you're looking at there. And then you get your emission spectrum. And you'll notice about the emission spectrum is what we've said before. Where I see emission, whatever photon was released. So let's have a look here. Every time I see a color, that is a photon released. Every single time we see a little color, that is an emission spectrum. Wherever we see black bands, it means those colors cannot be emitted for that atom. So these are the photons released for a specific atom. What is the emission spectrum? When energy is absorbed by electrons of an atom, electrons move from lower energy levels to higher energy levels. These excited electrons have to radiate energy to return to the ground states from an excited state, which is unstable. The emission spectrum is formed by the frequencies of these emitted lights. So emission spectrum means we take a hot gas and we energize it. It goes through a prism, and then you get a spectrum of light, right, specific to that atom. Right, the atom is the atom of the hot gas, not the prism. It's going to release a bunch of lights. That would give you your emission spectrum. Let's not forget here, over here. Oops, I should use a better color for that. Over here, there is a discharge or a photo tube. And over here where the switch is coming in is electric current. That's what's going to energize it. And when it passes over here, can you see this here? There is a prism. Let's just make a note there. When it passes to a prism and it's analyzed, we can get a certain kind of spectrum coming out from there. When we look at hydrogen gas, we said we get a high voltage. So electric current means high voltage, sorry. I just want to make sure that you guys have enough information. And then you're going to get these 4 colors, and each one corresponds to its specific wavelengths. And we've already looked at how that kind of formulates. Also, you need to understand that when an electron makes a transition means it falls from higher to lower, to a lower energy. Then we know a photon is emitted. I just want you to know that the energy of the photon is equal to the difference in energy between the 2 energy levels. Please make sure you get that written down in your books. We also know that no 2 elements have the same line emission spectrum. The line emission spectrum of an element is like a fingerprint of that element. So often we find that astronomers are able to analyze light coming from distant stars and then identify the different elements that are found in those kind of stars. Right, with the absorption spectrum, what we need to understand is that white light is passed through a cold gas. Oops, where am I spelling cold? Cold gas. And it passes through a prism, and then you get an absorption spectrum. Now this cold gas over here can be, for example, a hydrogen gas at low pressure. Alright, this little bit over here is a prism, a glass plastic prism here. What you'll notice is when I have absorption, let's think of hydrogen. So this is what we would get from hydrogen. So if I'm looking at hydrogen, notice that where the absorption takes place is exactly at the same wavelength where the emission takes place. Except when the absorption takes place, you have all the wavelengths of visible light are present, are present in the spectrum, except for 4 distinct wavelengths. So make a note there. All wavelengths are present in the spectrum except 4 distinct wavelengths. And the same wavelengths that hydrogen emits from a gas discharge tube or from that photo tube are missing in the line absorption spectrum. So look here what's missing. From emission, I've got violet, purple, a darkish blue, a turquoise blue, and red. So whatever the atom, whatever light, the atom emits, it also absorbs. Right, so as your white light passes through that cold hydrogen gas, the electron in the hydrogen atom absorbs energy of a photon of violet light, and it makes that transition. So if I'm looking here, just make a note of that. You've got your white light, it passes through the cold gas, then your hydrogen atom, let's say for violet, it absorbs, it absorbs the energy of a photon of violet light in order to jump to a higher energy level. For example, it would move from n is equal to 2, and it would jump to n is equal to 6. And that is how you get that little dark band over there. So your wavelength for violet light, we know, is about between 410, around 410, and it's being absorbed by the electron, and therefore it does not pass through the cold gas. So if we have absorption, right, if we have absorption, it means that the photon does not pass through the cold gas. And notice that the energy of the incoming photon must be exactly to the energy difference between those two levels. Maybe I should write that down over here. That the energy of the incoming photon must be, we spoke about this, exactly equal to the energy difference, exactly equal to the energy difference between the two levels. If the energy of the photon doesn't match that exact energy required to make that upward transition, we know it's going to fall back, or it's going to ignore the photon, and the result is only the photons with specific energies will be absorbed by the electrons in hydrogen atoms or any other different type. Let's have a look here. It says what is absorption spectrum? And absorption spectrum is the constituted by the frequencies of light transmitted with dark bands when energy is absorbed by the electrons in the ground state to reach higher energy states. And remember, the energy that must be absorbed must be specific energies with exact values. Alright, so that's the end of this video. I hope we understand absorption and emission spectrum. Please have a look. There is an activity called absorption and emission spectrum activity. Please make sure that is done before you come to school on Wednesday.